So this little diddly is all about torque. Now you might say, hey, what's this building thing and what does that have to do with torque? Well, since this Leaning Tower of Pisa is not tipping over, there actually is no net torque acting on the thing. So the reason it's not tipping over is because when we see where the center of mass of this building is right over there, it's not beyond the final tipping point over here. So as long as the center of mass rests on the inside of a fulcrum or point where you can teeter and totter around, it's going to stay upright. But once the center of mass shifts to the outside of a place it's going to teeter or totter around, over goes the object. So that's kind of the rule of how things topple or not. Depends on where that center of mass is. And those are the exercises that we were doing the other day, standing on our toes and touching our toes. And we're looking at where your center of mass is compared to your tipping point or the fulcrum where you're rotating around. So as long as your center of mass is behind that, it keeps it back on the other side. And of course, it's not even close to tipping the other direction on the other side, so it doesn't topple over. Well, the big news today is torque. We're out of American letters. That's where I'm going with that little tau, that Greek letter over there. And officially, it's a cross product. We use an R here instead of the D, but it's common to use a distance for the distance between the fulcrum, the point where you rotate around, which is the center of this little bolt there, which the nut surrounds it, and the center of that thing, not actually the edge of this thing like they're showing. It's actually the center of that to the center where the force is, the hand over there. And there, of course, they're using the perpendicular symbol for the perpendicular force. So sure, there's a trig function that normally goes out here. I never use the trig function outside of there because people get confused and they throw in any old angle for that trig function, and it doesn't work that way. Just make sure the force is perpendicular to this lever distance here, or this radius right here. That's why we prefer to use an R right over there. Okay? So in this case, if it doesn't move, there actually is no rotational acceleration because the torques would be balanced. This torque of this person pulling this way would be balanced by the counter torque of this nut, or the friction pushing the other way, not allowing it to happen. Now if this torque is greater than that frictional torque of that nut on the bolt, then there will be rotational acceleration because it's an unbalanced torque causing that to rotate or accelerate in one direction. So that's where we're going with the whole thing. So a torque is like a force. It's a rotational force. And if it's an unbalanced torque, it'll cause something to accelerate, but in a circle causing an angular acceleration, which they're calling a rotational acceleration. It's all the same thing. You just accelerate through an angle is all. So there you go. It occurs when a force is applied to a lever. And the unit is, they're calling it a Newton meter, which that's what we use for work, and I hate that. I call it a meter Newton, so it's a little less confusing. It's not work, because if this doesn't move, there's no work done. If this moves through an angle, then work is done. But you don't have to move for there to be torque. Okay, so it gets a little confusing because it's the same unit whether it's moving or not moving. So I use meter Newton and use the R cross the F, which that's actually what it officially is. Alrighty. So to find the torque, it's just the perpendicular force times that distance from the center of rotation where that little fulcrum would be. Think of a little like teeter-tottering around that point. And so here, let's see if I can draw here. So in reality, what's going on here? Well, I thought I was drawing and I was wrong. Okay, so you try that 7 more times. Okay, I am drawing this time. So this is like the teeter-totter point right over there. And there's actually a little lever on this side. And the big lever is on this side, clear to this person's hand over there. So this lever is much larger than this lever. Now if nothing moves, that means this force here, like this person pulls up on this thing, that means there's a great big force that keeps that from moving. Okay? that means there's a great big counter force, a huge force that keeps that moving. And how do I know that's a huge force that keeps that thing from moving if it doesn't move? Because look how small that R is. If it doesn't move, that means this torque from this hand is balanced with this torque from maybe all the rust or whatever is keeping this nut from moving. Because that's a very small distance, meaning a great big force, if the torques are balanced. If the torques aren't balanced, if this torque is larger than this, and that's not a great big force, then that's when the whole thing moves and it accelerates that way. Okay? Alrighty. Erase all ink on the slide. There we go. And there we go. Alrighty, next slide, please. So there's the fulcrum is right there in the middle, is what that's all about. Alright, so it only matters the perpendicular component. So if you're pulling this way, well, that's not, you have to use some trig to calculate the component that is perpendicular to that lever distance. Okay, that distance from the radius from the center of rotation to where the center of that force is. Okay, so one way or the other, the force has to be perpendicular to that lever distance. No torque going on here because there's no perpendicular force. There's a force on the wrench, that's for sure, but not a torque. Okay, zero twist on that nut in that case. No torque at all. All right, so if you increase the lever distance, what happens to the torque? Well, more torque, because it's this longer distance, same force, greater distance means a greater twist onto that nut. Applying more force actually puts more twist on there as well. So the bigger the F, the more torque or twist on there. How much more torque would you have if you apply a parallel force at distance below? Zero torque. So it's more pushing force onto the thing, but that doesn't cause rotation because the force is at the center of mass of that thing. If the force acts right at the center of mass, there's no twist. Zero twist, there's zero torque onto the thing. Oh, well, there's the answers. Ta-da! Alrighty, guys, there's the drawing. 4 equal forces, 100, 100, 100, 100 on each one of those. Which of those 4, pop quiz, exerts the greatest torque and why? Which is the least torque? Give you some time. Dum 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 dum. The answer to number 1 is C, because it's got the greatest lever distance. Okay? And you might say, hey, B is about the same lever distance, but it's at an angle. When you do the trig to find out what that force is straight down, it's a smaller amount than C. D, there is zero torque. That's the smallest amount because it's zero. There's no torque. There's no lever distance whatsoever. The force is at the center of mass of the thing. There's absolutely no twist on that nut whatsoever. So D is the biggest loser of them all. There is no torque. A is the next to the least torque because it's such a small lever arm there probably. And so that would be a little less than B, because B is not at a great angle, but the lever arm's still pretty big, but it's at a slight angle. That's why it's still less than the C. Alrighty, there you go. Ta-da! Alright, there's Ned. Ned's tightening a bolt on the car. It's 12 newtons and 0.4 from the fulcrum. What's the torque? It's 12 times 0.4. Okay, 4.8 meter newtons of torque. Okay, there you go. Hey, they like to balance. Look at that. You got a 400 at 1.5. That means if you're 200, you're twice the distance. That's balanced torques, right? So that's the exercise we already did. If you're half the mass, you need to be at twice the distance to have the same torque. So that's 200 times 3, that's 600. 400 times 1.5, that's also 600. Meter newtons of torque, they both balance each other. Okay? There you go. So we've actually already done some of this stuff. So the clockwise torque, going the same direction as a clock, which is this fellow over here at the 1.5 meters, is the same as the counterclockwise, the gal over here, going the other direction. So the two torques balance out. So half the force but twice the distance is the same torque as on the other side. So there's no rotation. because you have balanced torque, or if there is rotation, there's no change in speed of rotation. There's no angular acceleration because the torques are balanced. Remember, a torque is like an angular force. If all forces are balanced, there's no change in velocity. If there's no unbalanced torque, there's no change in angular velocity is the key. Alrighty. So, hey, they must think we're silly and we don't remember what this distance is. Well, it's twice the weight, it's half the distance, 1.5. Okay, so we just saw that example. Alrighty. We're getting more complex here. Okay, sum of all torques. Okay, so you can have more than one object on one side. That's what they're showing you here. You can have several objects on one side, several on the other. You don't add the forces and then the distances. You add the forces times the distance, or the torques. You add the torques together on each side. So you got to find the torque of where every mass is at every distance. Now, yes, it works to do the masses because since you're all on the same planet, you can divide out by the G thing and do it with masses, and it works just fine. Okay? Oh, was that what they were showing back here? Nope, they just did the forces there. But it all works with masses as well, because you can divide by the G thing in every term, and it changes that to a mass in every case, and it works just fine. So to find the center of mass, that's the point we consider all mass to be located. Remember that. The center mass is the point where you can consider every bit of mass to be. Sure, there's wood there. Sure, there's wood there. But if the person's balancing the wood on that point, it's just like all the wood is there. It could be. Just as well be, because it's acting right there. All the weight of the wood is acting right there. So even though there's wood here and there's wood here, we can say all the wood is acting like it's here. Even though it's all over the place, it's going to make our math easier in a moment if you remember that all of the mass of the wood acts as if it's at its center of mass. It really simplifies our math here coming up in a second, okay? Alrighty, so remember that fact, Jack. Alright, so the center mass does not have to be within the object. It can be out. High jumpers, when they jump over the bar, they bend around their body. They're actually, if they're a good high jumper, their center mass actually passes below the bar. Not by a lot, but by a little bit as they wrap their body around their pole vaulters, same idea. So the center mass does not have to be within the body. That's non-uniform center masses. Okay? You're a non-uniform center mass. So here we go, guys. Here's someone's tossing a wrench just because they're a wrench tosser. That's just part of their personality. Now they mark the little white dot where the center mass is, and you might say, hey, how do they know that's the center mass? They balance it on their finger. So they balance it on their finger, and they notice that means that's where they balance it, so it's like all the mass acts there. It says you toss this wrench at somebody for whatever reason. Maybe you toss it at a monkey because it's a monkey wrench. Aha, I don't know. But whatever, the point is, this center mass goes in a trajectory that any rock would or anything else. Even though the handle flies in a big circle like this, the center mass follows the path that any kind of rock would. Alrighty, so here we go, guys. So you notice the stick is hanging from the center of mass of the stick. So because of that, it's like the wood does not add any torque to the system. Because it's hanging from the center of mass of the wood, you don't have to include the mass of the wood as part of the torque. It's already pre-balanced. You only have to consider the external torques, which are these two masses. And as you have a 20 that's located at, this is 50, so it's 10, 20, 30. So that's 30 times 20, that's 600. Then you have to have 600 over here at a 10, 20, 30, 40. So, you know, that's 40 times your F, and that has to equal the 600, right? So we don't have to worry about the mass of the wood yet. That's coming in our next problem in a moment here. So you set it up, your 20 times your 0.30 if you want to be in meters. It's at 40 centimeters or 0.40. It's 15 newtons. Okay? we're going to stop right there because this problem, it gets a little crazy. All right, get ready for some craziness.